Hello, hello. Funny behind the scenes. I started talking and I didn't properly click the record button. So we're taking it from the top, folks. Okay. So this is going to be our day 3 material. We are learning derivatives of trig functions and the chain rule. First, just some ideas that we need to recall for trig functions. We have first sine and cosine. They help us define tangent as seen here. And with sine, cosine, and tangent understood, we have reciprocals of them. So cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. And then just because of that technicality, cotangent can also be defined using cosine and sine. Then we have some Pythagorean identities. Sine squared plus cosine squared is equal to 1. Divide both sides of this equation by sine. You'll get that equation, divide both sides of this equation by cosine, you'll get this equation. Example 1. Using a unit circle, find the following values. So, if you draw this first quadrant of a unit circle, you could see that cosine of pi over 2 is just 0, and sine of pi over 6 is just 1/2. Now, Um, just a quick recap of this. You know what? Well, I didn't write it, so I guess it's a good thing that um for these values, we know that they take a number between 0 and 1. In between these are the way I like to write them is I write 1/2, 2 over 2, and 3 over 3. And then I just write a square root on top of every one. And then you tell yourself, okay, oh, 2 over 2, excuse me. 3 over 2. And then you just say yourself, okay, well, that can be simplified to 1/2. From there, you recall that cosine is your x term, and sine is your y term. So, if I start with the circle, and I just move it up, where is it longer out towards? Is it longer out towards horizontally or vertically? The answer would be it's longer out horizontally. So you start with the bigger value, square root of 3 over 2. And then you just count 3, 2, 1, and then 1, 2, 3. And then you read 0 and 1 respectively. This pattern repeats as you draw the rest of the unit circle. For C, so like what I did, right, is I did it in blue. I answered A and B. And then C, I did in purple. And I answered that just getting it from the fourth quadrant. Then, after getting it from the fourth quadrant, you are asked to get 7 pi over 6. So 7 pi over 6 is in the third quadrant. And I was just drawing the rest of these. So let's go ahead and do the rest of these. For here, we have 3 pi over 4. 5 pi over 6. 7 pi over 6. 5 pi over 4. And then, give me a moment. 4 pi over 3. Okay. And then this is going to be 3 pi over 2. And I forgot to mark this one as pi. So you can see sort of symmetry play out. It depends on how you guys do it. There's multiple strategies for remembering the unit circle. Um, I don't. Hmm, I don't think I'm gonna get too strict about this, but at the same time, we do need to know it. Especially because as we're doing more of this math, it's gonna be, we don't want to waste time on inputting a unit circle in the calculator, unless you have the time. And also with this test, I still haven't decided if you guys are gonna use a calculator. I'm probably gonna ask you for a lot of like open functions. So I might just take off calculators altogether just because there's some calculators that can do these derivatives and integrals for you. But I still haven't decided. I'll probably tell you all in either Thursday's video or just the announcements. Okay. Well, anyway, we see that we're doing 7 pi over 6. Thus, the sine value, which is technically the negative 1/2. But there's another negative. So it becomes double negative, so it's positive 1/2. And that would be your final answer. Now, this is just recapping the review. Like I said, we don't need to get too much into this. This is ideas that I'm kind of expecting you to know from pre-cal, but we are touching on them very quickly. So keep that in mind. All right, let's talk about the limit. Now, we're not going to analyze the limit with the definition or with the derivative just yet. We're just going to analyze it with the graph. So, as we look at this sine graph, and you ask yourself, okay, what's the limit as x goes to infinity, either positive or negative? We know that it's going to be bounded between 1 and -1, but it's going to keep this sort of wave that's repeating. So that means that this does not exist. This limit does not exist. How about for cosine? Cosine has the same feature, unfortunately. This limit also does not exist. Now, the derivatives of sine and cosine functions. For any function f of x, the derivative is f prime is equal to that limit, just the limit definition of derivative. Now, the gimmick here with sine and cosine is that recall that it's the logic of drawing a slope of the tangent line. So, you are drawing a slope of the tangent line. What's the slope of tangent line here, and here, and here, and here, and here? And it starts increasing, then maybe stagnant, decreasing. Okay? So that means the slope is positive. It's increasing. And then the slope gets more narrow. So it's still positive, but it's just not that narrow. And then it's at 0. And look, at the hill, the slope is also at 0. And then the slope starts getting more negative, more negative, more negative, more negative slope. And look, you're at a negative bound over here. Now, keep that in mind, that limit definition in mind, or not the limit definition in mind, excuse me, but that tangent definition in mind. Now, visually, we see that if we were to draw or keep note of the function's slope, that it is technically just recreating the other trig function, cosine of x. So the derivative of sine of x is cosine of x. Let's look at cosine. Cosine at 1 has no slope. Over here, we note that by putting that point in the middle. And then, as it goes to the right, it starts having a negative slope. Here, we see that it's starting to have a negative slope. But, as we reach pi, the slope still stays negative. But, it gets real steep, and then it turns about at the negative. And it becomes flat again. And look what this is. it's marking that the slope is 0. And over here, the slope is indeed 0. What is this trig function, you ask? Well, it's actually our sine function, but not exactly. We can see here that we start a sine function typically by going up, then down. Here we went down, then up. So in order to just account for that, we're going to put a negative on that sine function. So this is just the bona fide result we need to take from this. The derivative of sine is cosine, and the derivative of cosine is negative sine. Let's go ahead and practice these with a couple of things that we have already learned by this point. Find the derivative of j of x, which is defined as 5x to the third times sine x. Recall the product rule. Okay, so we're just kind of redoing some old examples, but now with the inclusion of trig. Let's label f of x 5x to the power of 3, and let's label g of x as sine of x. The derivative of 5x3 is 5 times 3, because we're bringing that 3 down, times x, take off a power, to the power of 2, which is just 15x squared. Sine x, well, we know that's just going to be cosine of x. So, setting up the answer, we have 15x squared times sine x plus cosine of x times 5x cubed. Let's keep it moving. We have sine and cosine multiplied here, so let's label one as sine of x, and the other guy cosine of x. The derivative of these is just transparent. And we have cosine of x times cosine of x plus sine of x times negative sine of x. From here we have cosine squared of x minus sine squared of x. We could simplify this further if you like, but that's kind of not the point. Right now it's kind of like what we were doing last time where we just want to see the patterns hit. Example 4 shifts it just a little bit. Example 4 says the derivative of j of x, that's equal to cosine x divided by 4x squared. So, and recall the quotient rule. So let's go ahead and define f of x. Now, specifically using this formula, f of x is going to be that top part, cosine of x. The derivative of that is sine x. That means g of x is 4x squared, and that derivative is 8x. So we could plug them all in together. We have negative 4x squared sine of x minus cosine of x times 8x over 4x squared, all of which is squared. And there you go. Now, derivatives of other trig functions. Let's start off with an easy one to show. Recall that tangent is a sneaky way of writing a fraction for these cosine and sines. It's sine of x over cosine of x. So we can just copy and paste that product rule idea. F of x is sine of x, and its derivative is cosine of x. And then g of x is cosine of x, and its derivative is negative sine of x. So that means our answer is cosine of x times cosine of x minus sine of x times a negative, so I'm going to make that positive now, sine of x, all divided by cosine of x squared. This can be rewritten as cosine squared of x plus sine squared of x over cosine squared of x. And that top part just becomes 1. And then with product properties, we know that this can technically just be written as secant squared of x. This leads us into the derivatives of all 6 trig functions. Technically, you could prove them all, but I just wanted to prove one with you guys. Noted to you guys that the other proofs do exist. They're not, these crazy abstract math ideas, but just show one, just say like, hey, they exist. Okay. We didn't just make this up. Alright. For sine of x, it's cosine of x. For cosine of x, it's negative sine of x. For tangent of x, it's secant squared of x. For cotangent, it's negative cosecant squared of x. Secant is weird. It has secant of x, tangent of x. And then for cosecant, it's negative cosecant of x times cotangent of x. With all these derivative rules in mind, let's go ahead and try a bag of mixed problems. Let's start example 6. Find the derivative of j of x, where j of x is equal to cosecant of x plus x times tangent of x. Okay? So for here, this is just the addition property first, where we're doing cosecant of x, we're doing this guy's derivative, and then plus x times tangent of x. Doing that guy's derivative. This one is just straightforward. It's going to be negative cosecant of x times cotangent of x. And this one, we would have to use the product rule. I'm going to do derivative of x first, and we get 1 times tangent of x. And then derivative second guy next, x times the derivative of tangent of x. I'm going to fill in that last derivative while trying to give myself some space. Negative cosecant of x times cotangent of x plus tangent of x plus x times secant squared of x. And that's your answer. Example 7. Find the equation of the line tangent of the graph f of x cotangent of x at x is equal to negative, x is equal to pi over 6. Well, recall that this line tangent idea, m tangent, is just the derivative of that function. So let's take the derivative of that function. That's just probably going to be negative cosecant squared of x. But now we need that specific coordinate. Well, Oh, we're gonna have to find the whole equation. So technically what we should have done first is just plug it in. Cotangent of pi over 4. I don't know the cotangent off the top of my head, but I can just split this up to its definition. Cosine, oh, it's going to be 1 then. Let me keep going. Cosine of pi over 4, sine of pi over 4. For the pi over 4s, they both have the luxury of being the same thing. Square root of 2 over 2, square root of 2 over 2, which is because the same thing, the answer is 1. Okay. Now, let's go ahead and, with this derivative done, we're going to plug in f prime of pi over 4. Negative cosecant squared of pi over 4. Let's rewrite this in terms of its sine definition. Sine squared of pi over 4. Well, sine of pi over 4, excuse me, is just the square root of 2 over 2. So, let's apply that square. 2 over 4. And then let's go ahead and correct this fraction. Multiply both the top and the bottom by 4. Negative 4 over 2. And that's going to be negative 2. So my slope is negative 2. So if I'm just to plug it in to the classic point slope formula, I get, I didn't write my coordinate, pi over 4, comma 1. Minus 1 is equal to negative 2, parentheses x minus pi over 4. Let's go ahead and distribute that negative 2. Negative 2x plus pi over 2. And then we add the 1. Negative 2x plus pi plus 2 over 2. And that would be your answer. Actually, you maybe didn't even need to combine the fraction of all. I probably would have taken this as a correct answer. If you just wrote it like that without combining the fraction, to me that's fine too. But I'll leave you guys to decipher that. Okay? Now, we have to point out a technicality with the sine and cosine derivatives. If you take the derivative of sine, you get cosine. If you take derivative of cosine, you get sine. Now, we didn't talk about the derivative of negative cosine, but we know that via the constant property for these derivatives, we can just pretend that's not there and add it back in. What's the derivative of sine? Cosine. Now plug in the negative. Same idea. We don't know the derivative of negative cosine, but we know derivative of cosine, which is negative sine. So technically, right, I'm going to do this in an erasable pen. We would have had negative. But if we carry the previous negative, it would have been a double negative, which made that positive. Now, the thing you should notice at this point is that we're back at sine. So we have a unique case with these set of functions where the derivative repeats itself. So, for example, if you applied a derivative mod 4, right, because it jumps back after every 4 to the sine function, then that derivative is just going to be sine. However, if you perform this derivative, 1 mod 4 means you do as many 4s, but then you add just one more at the end. Because of how it repeats, you're just going to get cosine of x. Similarly, for cosine, if you just keep going in 4s and keep repeating it that way, if you start cosine 1, 2, 3, 4, you end at cosine. And then, if you do 1 mod 4, means that you'll keep going in circles, but then you'll at the very end jump 1, which would be negative sine of x. So let's go ahead and do these ideas together. We have find the 14th derivative of cosine of x. Well, we know that 14 is can be rewritten as 4 plus something times plus something else. Well, the closest thing I can see is a 3, because that would be 12, and 12 plus 2. So that means 14 will be 2 mod 4, meaning that we can count the cycle of 4 3 times. And then at the very end, after we count that cycle, we need to add 2. So 1, 2. So that would be negative cosine of x. Then we have example 9, which is a bit trickier. That says 74. Rather than figure out if that's divisible by 4 or not, I mean, if what it is to get to this expression, I'm just going to go ahead and divide it by 4. 74 divided by 4, 1. Only 1/4 fits into 7. That leaves a remainder of 3. Drag this here to 4. That's going to be 32 that will fit into that. So that's going to be um 4 times 8. And you're left with 2. So that means that 74 is 4 times 18 plus 2. So, just like before when we talked about that second trick, or going however many cycles of 4, but then we go 1, 2 after cosine, this guy's also going to be negative cosine of x. How about over here? Now we're going to go ahead and apply some of these to sine of x. Similar idea. I rather just get out the groups of 4 right now. We know that 1 4 exists in the 5, and then we have left 19. And we know the closest thing we'll get to this is 16. So you'd be left with 3. So that means from sine, you'll go 14 cycles of 4, but then at the very end you go 3 steps. 1, 2, 3. Into negative cosine of x. Over here at 62, similar beef. Only 1 4 fits in the 6. And we know here that at most 20 will fit into this 22. Now starting from sine, we're going to go just 2. Because we'll go 15 cycles of 4, but because it's a cycle and it repeats, we don't actually have to denote that. So we just go from sine and we go 1, 2. Negative sine of x. Okay, that's going to wrap up our trig functions. Next, let's talk about chain rule. Now, chain rule helps us in particular when functions get a bit ugly and we're just writing math on top of math on top of math, or I should say, inside the math. So for example, let's let f of g of x means we first apply g to x and then we apply f to the result of g of x. This is a composite function. So for example, if I have f of x defined as 3x squared and g of x defined as x plus 4, then this can be rewritten as 3 of x plus 4 squared. Now, let's talk about outside versus inside functions. It's the same idea, but it's going to help us label what we need to better understand this composition trick. So this is sort of a review. Let's go ahead and label the outermost function for all these 6 examples. Well, the outermost function seems to be this 8th power. For now, let's go ahead and use u, since we're going to denote that as the inside function. So u to the power of 8. Over here, similarly, we have u to the power of 4. Here, the outermost is that sine function. Here, the outermost is the exponential function. The outermost is that square root. And here, the outermost is that ln. Oh, I accidentally wrote an x for this as well. All right. Now, let's talk about the inside function. So what is that u? Visually, from here to here, what is that u? Example 1, that's just going to be 5x3 minus 2x plus 7. Example 2, what's being taken to the 4th power? This whole expression, x squared plus 5x minus 1. Over here was sine being taken of 3x. Over here was the exponential 2, x squared. Here, what's inside the square root? X cubed minus 1. What's inside the ln? 3x squared. Now we have a better idea, hopefully by this point, of... Oh wait, is there more on the next page? I think there is, actually. Yeah, I just looked at my key and I saw that there was more. Okay. What's the outermost function here? This one is just going to be that squared. Oh, sorry. And this one is going to be 1 over u cubed. What's happening innermost here? Sine of x. And the innermost thing happening here is that 3x squared minus x. Now the chain rule. The chain rule for composite functions is defined as the derivative of the outermost composite function retaining its input exactly the same, but then multiplied by that input's derivative. So keep in mind, we're going to do that same pattern where we denote our inside and our outside, and then the derivative of both. And then we're going to stack them as you see here. So let's start with this one. Recall we said the outside function was u squared. And the inside function was sine of x. So what's the derivative of that outside function? 2u prime. What's the derivative of that inside function? Cosine of x. Next, this one, I think they're all, I believe they're all copied and pasted. Well, I don't know why, we don't need to copy and paste it thoroughly, but same idea. The outside, u4, square root of u, 1 over u to the power of 3. Their derivatives are 4u cubed, 1 over 2 square root of u prime prime. And then this one is going to be, hold on. Now for my convenience, I'm going to rewrite this just so it tracks better for me. And it's going to be negative 3, 1 over u to the power of 4. All right. Now the innermost. X squared plus 5x plus minus 1. That derivative is going to be 2x plus 5. Over here, x cubed minus 1. That derivative is going to be 3x squared. Over here, we have 3x squared minus x. That derivative is going to be 6x minus 1. Now, let's construct all of these derivatives. So, you take, let me use a different color pen for this. You take that f prime and just write u that's inside of it. Why did I do u prime? I think I was getting too lost in the sauce. The u prime becomes like sort of related when you're doing implicit differentiation, but right now we're just doing this sort of strategy, so ignore the prime for now. I didn't write that. Okay, good. All right, so for here, derivative the outside 2u, so 2 times sine of x, and times the derivative of the inside, so times cosine of x. Okay, pretty straightforward. Um, that is so funny. Okay, I made a mistake. So I thought this and this was the same thing. But look closely. That square is next to sine. This square is next to x. So this is actually incorrect. Let's go ahead and let's do both, I guess. Here. Actually, I'll just write the derivative here. No, let me go ahead and just both. Just erase the mistake technically, right? What typo? There's no, or what different problem? There's the same problem, he says as he whites out everything. But we can still, on the back of this paper, redo it. So again, j of x is equal to sine of x squared. The outside function is sine of u, and the inside function is x squared. The derivative of the u is 2x, and the derivative of the f is cosine of u. So let's plug it in. We got cosine of u, which is x squared, and times u prime, which is 2x. And that would be your answer. Right. Bonus problem, I guess, right? But let's keep it going. Over here, we start off with the derivative of the outside, plug in u. So that's 4 parentheses x squared plus 5x minus 1 to the power of 3 times the inside derivative times 2x plus 5. Right? Let's keep it going. Derivative outside with plug in u, we have 1 over 2 cube root of x squared minus 1 times that inside, so it's a 3x squared. Over here, last one, -3, 1 over parentheses 3x squared minus x to the power of 4, and then times the derivative of what was inside. So times 6x plus, or sorry, minus 1. Just double checking my answers. Okay. All right. Example 13. Find a derivative of 2x plus 1 to the power of 5 times 3x plus or minus 2 to the power of 7. So for here, we have the technical issue where we have to, for our benefit, stack the chain rule on top of each other. Now, technically speaking, you don't have to, right? We can distribute these powers and simplify and etc., but that'll clearly be a lot of work. We rather just simply do it the sort of forward way. Okay. So f of x defined as 2x plus 1 to the power of 5. And g of x is defined as 3x minus 2 to the power of 7. So what is f prime? Well, take the derivative of the outside function with respect to its insides, then multiply derivative of its insides. It's going to be written as 10, parentheses 2x minus 1 to the power of 4. Over here, similar situation will occur. You'll have 7. Or here, I was actually using a different shade by accident. Of 3x minus 2. Knock one power down, and times derivative inside, which is just 3. So 21, parentheses 3x minus 2 to the power of 6. Okay. Now from here, you're just going to go ahead and do the product rule. So let's go ahead and do the product rule. We have 10, 2x plus 1 to the power of 4 times 3x minus 2 to the power of 7 plus 21, 3x minus 2 to the power of 6 times 2x plus 1 to the power of 5. And that would be your answer. Keep in mind all of the bits and pieces that we plugged in. So this was f of x, this was g of x, this was g prime of x, and this was f of x. All right, we're almost done. The chain rule has the ability to go on indefinitely. You can take a function with a function within a function within a function within a function. However, the example I chose to just include is just when we have 3. So the composite of 3 functions is defined like so. Or not the composite. The derivative of the composite 3 functions is defined like so. Example 14. Find the derivative of cosine to the power of 4 of 7x squared plus 1. Okay. Well, let's see. The inside most of this guy has got to be the 7x squared plus 1. And right outside of it is a cosine. And let's just use of the the inside, U. And then the outermost part is just that V. Now we're using to be inside to the power of 4. We're taking all this to the power of 4. Its derivatives are 4V, V to the power of 3, negative sine of U, and then 14x. Now let's just stack everything next to each other in its appropriate formula. So you start off with the derivative of the outermost guy. Wait. Oh, I see what happened. Let's call this F, just so it's not confusing. So F's derivatives right here, and then we're just plugging in what V and then with what U was. So we have 4 parentheses cosine of 7x squared plus 1 close to the power of 3 times now the middle function's derivative with what was inside it originally, so negative sine of 7x squared plus 1. And then now multiply the derivative of the inside, the most inside, 14x. And that's your answer. Let's do the last one. The last one, we can see the insidemost function is x to the power of 3, followed by a sine of x, followed by an, or I should have wrote of u, but then followed by v to the 6. The derivatives are 3x squared, respectively, cosine of u, and then 6v5. Okay, let's go in order. 6, plug it in with what v was originally, which is sine of x to the power of 3, all of which is to the power of 5, times cosine of u, which we saw was x cubed, then times that innermost, which is just 3x squared. And that's the derivative. All right, this is going to wrap up today's lecture. Let me know if you guys have any questions. We did sort of rush through the unit circle portion. So if we need I'm gonna be honest, if we need a video on the unit circle, let me know as soon as you see this so I can try to make one and slip it in as quickly as possible before the final. Okay? Again, let me know if you guys have any questions. I'll see you all in the next one. Bye bye.